The machine learning models are essentially data-driven models. To construct them, we need some accuracy measure. Let's introduce loss function. By definition, the loss function or cost function is some measure of predictive inaccuracy of the model. Loss function is calculated with respect to the instance x, y, where x is the model's input and y is the model's target output. If the model has no error on the instance x and y, then the loss function will be 0. And the more mismatch between model's output and target value, the greater will be the loss. Let's introduce a statistical model of the data. It's typical in machine learning to assume some statistical interpretations to derive some formulae or prove theorems. Assume that the target mapping is not deterministic. There are two reasons of this. First, the object under modeling may be stochastic. Or second, the input vector may be insufficient to determine the output value. In both cases, we'll obtain different objects' outputs for the same input vector x. That is, the output y for given x is a random variable drawn from the conditional distribution f of y conditioned by x. Also assume that the input x is a random vector drawn from some distribution f of x. Applying the well-known formula from probability theory, we write the expression for the joint distribution f of x and y. This joint distribution contains exhaustive information about the mapping under modeling, and in practice it's usually unknown. Indeed, if it were known, the machine learning wouldn't be necessary at all. Since input x and output y are random variables, and loss function is a function of x and y, then the loss will be a random variable too. And for now, we introduce the term risk of the model. By definition, risk associated with the model is expectation of its loss. The formula is presented here. If the joint distribution f of x and y were known, we could fairly calculate the risk. But since it's unknown, we estimate it. It's known from mathematical statistics that the best estimate of the expectation is a mean. And we have data sample D drawn from joint distribution f of x and y. And we will use it to estimate the risk. The obtained estimate is called as empirical risk. Empirical risk represents a error of model over training sample. There are many loss functions used in the empirical risk calculation. For example, the quadratic loss function that's presented here is used in regression tasks. And 0,1 loss function is used in classification tasks. There are many other types of loss functions that we'll consider later. The objective of any learning algorithm is to minimize the empirical risk over the hypothesis from the given hypothesis domain. The machine learning problem is in fact the empirical risk minimization problem. Let's consider risk for quadratic loss function at given x. It's a random variable because the target y for a given x is a random variable drawn from distribution f of y conditioned by x. We apply simple conversions and obtain that the risk is a sum of two terms. The first term is squared difference between model's output h of x, that's determined value, and the expectation of the target for a given input x. As it's known from mathematical statistics, this expectation as a function of x is called as regression function. So the first term is a mismatch between modeled function and a regression function. And it can be minimized because we can influence the function h of x by choosing the hypothesis from the given hypothesis domain. When we train the machine learning models, we in fact want to model this regression function. And the second term is the conditional variance of the target variable for a given x. Its value is completely related to the mapping under modeling. We can't influence it and consider it as a noise. The hypothesis h is a result of learning algorithm mu applied to the training sample dt. This sample is usually randomly taken from the available data d. Since the hypothesis h depends on the training sample dt used, that's random, then the hypothesis h will also be random. It means that for a given input x, the output h of x and the loss will be random variables. And let's calculate its expectation. It should be calculated over all random training samples dt. Analogously, we apply simple conversions and obtain that this expectation is a sum of two terms. The first term is the square difference between expectation of the random model's output and the value of regression function for a given x. This term is called as statistical bias of the model f at given x. The second term is the variance of the model's output for a given input x calculated over random training samples dt. It's called simply as the variance of hypothesis h for a given x. So the risk of the model for quadratic loss at given x can be decomposed into three terms that are squared bias, variance, and noise. Bias and variance are related to our model, and the noise is unavoidable error related to the mapping under modeling. When we define an inductive bias, we determine trade-off between bias and variance of machine learning model. So if the inductive bias is too weak, then more probably the model will be capable to represent a complex function that passes exactly through the given training instances. And the result will be highly dependent on the particular training sample. It's illustrated in the left figure. In the case of overfitting, for every new training sample, we will receive new learned function that passes exactly through new training points, and hence we will receive high model variance. In the case of too strong inductive bias, for example, for the class of linear models, there are almost no dependency on the particular training sample. We will always obtain almost the same line. It means that the model almost has no variance. At the same time, it can be noticed that the mismatch between any trained function and regression function is high. So this linear model has high bias and low variance. And if the inductive bias was defined properly, then the model will have low bias and low variance. It's shown in the right figure. In this case, there is no dependency on the particular training sample, and the model has good generalization capabilities. Here, the inductive bias is defined as a limitation to hypothesis domain where the hypotheses are no more than quadratic functions. The concept of bias and variance can be illustrated with a game of darts. The dartboard is the space of models. Every dart, that's a green point, is a trained model, and the bullseye is the true mapping. For the case of model with high bias and low variance, we every time shoot almost at the same point far from the target. But if we have a model with low bias and high variance, we shoot very inaccurately but near the bullseye in the average. Here is an illustration how the bias and variance depend on the model complexity. Two simple models usually have low variance but high bias, and two complex models have low bias but high variance. The optimal model complexity realizes some trade-off between bias and variance. The same thing is with the generalization error. The figure shows how the training and test errors depend on the model complexity. Two simple model has both errors high. It's essentially underfitted model. With increasing model complexity, both errors tend to decrease because of decreasing bias, and from a certain moment, the test error starts to increase while the train error continues to decrease. It happens because the model's variance becomes unacceptably high and the model starts to adapt to the particular training data.